Hello, my name is Shaunak and welcome to my channel Physics for Students, and I want to make an important declaration before I start ahead with this video. As you can see right on the thumbnail that this is a fresh series of video which is named as episode 1. Now, ever since I started my channel round about 2 years back, I initially started only making videos on Einstein's general relativity and tensor calculus. Over the years, I tried to migrate to some other areas, including quantum field theory, quantum mechanics, classical mechanics, electromagnetism, Maxwell's equations, topology, differential geometry, and so on. But I am really thankful to you that your love, your cooperation, your comment has helped me to grow mostly on my general relativity videos. And as you know that I conduct on a monthly basis a free webinar on Einstein general relativity, which is happening every month, and you're free to join. Now the thing is that what I have found is that my earlier videos on general relativity are good. You have appreciated there are a lot of mathematics and good insights into it, but they are not in a proper episodic manner. There are subscribers from India and abroad who has many times put up a comment that, sir, your videos are not in an episodic manner, and I acknowledge the fact that it is not in an episodic manner. The reason was that I never had an idea that I would create a channel and then there will be so much of love and cooperation as shown from your side that I would take it seriously, and now I am doing almost on a daily basis on these videos. So what I am doing, an improvement on this is, number one, I'm making all these videos episodic. That means you will get a complete episode 1, episode 2, episode 3, so that there is a sequence and you really know that which episode speaks of what. And if you miss one episode, you can go back to the previous episode, learn certain things, and then again you can start with the new episode. Number two is that as a human being and a person learns from his or her own mistake, or I would say matures through the passage of time, so have I. And I know that there are certain limitations, I would say certain areas which are a little bit gray, which are not yet very clearly defined in my videos. Areas into parallel transport, geodesics, coordinate transformation, especially tensor calculus, differential geometry, some part which is related to general relativity. So what I am doing is that in this video I am expanding, elucidating, and I am doing a lot of internal study so that these concepts are much clearer, much easily understood by everyone. To do is that I'm making this episodic, I'm making it more detailed, and I'm making it absolutely easy using lot of graphs, icons, schematic diagrams, etc., so that the learning is not purely mathematical, it is illustrative and intuitive also. Although I have a separate playlist, I will make a separate playlist which is exclusively on the hardcore part of the mathematics of general relativity. However, these episodes will also contain mathematics, but it will be a complete understanding in a very detailed and a very lucid and easy manner. Now going ahead with that is what I just wanted to tell you. As you can see on the thumbnail, it is episode 1 where I would be speaking about the philosophy of general relativity, which is much deeper, and I have never spoken those in my video, and how we move from flat space to curved space. So without wasting much time, let us go and start with today's video.
In the vast cosmic theater of this universe, our understanding of reality has evolved dramatically over the centuries. From the simplicity of flat and unchanging space to the mind-bending concept of a curved and dynamic cosmos. Welcome to the first episode of our journey into the realm of general relativity, where we explore the profound philosophy that reshaped our perception of the universe. Today we embark on a quest to comprehend the essence of general relativity, a groundbreaking theory that takes us from the realm of classical physics, where space is a static stage, to a new reality where space itself is curved and gravity is not a force but a consequence of that curvature. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to the first episode of General Relativity for Beginners. Before we go ahead and understand and go deep into the subject, first we need to understand this. What is a system? Now don't worry, I'm not talking of any other system, but a system in terms of physics and mathematics, and why general relativity and system are intricately related to each other. Coming up in the next part of the video, what is a system? Now you see, the word system as usual is derived from the Greek word systema, or we can call it as a system, which is from the Latin word. So overall we can say that a system is a group of interaction or interactive or interacted related elements that according to a set of rules to form a unified whole. We can also say that a system in physics is a collection of objects that are interacting with each other. For example, it can be as simple as like a single object like a cricket ball, and it can be as complex as our entire universe. Now, systems are important in physics because they allow us to study the behavior of objects in a controlled environment. For example, it helps us to study the objects in a controlled environment. For example, if you want to study a simple as a single object, for example, you want to study the motion of a ball, we can create a simple, I would say, system consisting of the ball and a smooth surface, and by studying this system, we can learn about the laws of physics that govern the motion of the objects. So system as itself is a kind of a, I would say, a interaction of particles, a behavior which helps us to understand and even predict what is coming next. Now, systems are actually important in physics because they allow us to make predictions about the behavior of objects in the real world. For example, by studying the system of a rocket and its fuel, you can predict how far the rocket will travel. Now you might be even thinking that what are not a system, because we just talked about the system which allows to make us behaviors. It can be a simple object or a complex object, but are there something which is not a part of a system? Answer is a very yes. For example, forces. These are fundamental interactions between particles or objects such as gravity, electromagnetism, weak force, strong force. But forces are not systems because they are not composed of interacting parts. Fields are regions of space where forces are exerted. For example, the electric field around a charged particle is a region of space where other charged particles will experience an electric force. Fields are not a system because they are not composed of interacting parts. Constants of nature are fundamental quantities. For example, the gravitational constant, the speed of light, the reduced Planck's constant. Constants of nature are not systems because they are not composed of interactive parts. Symmetries. These are physical laws that remain unchanged under certain transformation. For example, the laws of physics are symmetric under rotation, which means they are the same for all observers who are rotating with respect to each other. Symmetries are not systems because they are not composed of interactive parts. So we have several other systems in physics which is not worth explaining here, but it is definitely worth mentioning. Mechanical system which deals with mechanics, thermodynamical system which deals with heat and work, etc. Electromagnetic system which we all know, and quantum system which deals with quantum physics, quantum computing and various other phenomena. Now this system that we talked about, why we are talking about system, will become very clear in a few minutes from now. But in order to know and understand actually how the system was formed, we have to turn the pages of the history. And in the 19th century, we go back to this French physicist Nicolas Sadi-Carnot, who actually studied thermodynamics and pioneered the development of what is called the concept of a system in the natural sciences. In 1824, he studied the system in which he called the working substance of steam engines in regard to the system's ability to do a work when it is applied in heat. I very recently made a video on thermodynamics talking more about the achievements of Sadi-Carnot. You can go ahead and look into it. Now this gentleman, the biologist Ludwig von Bertalanffy, became one of the pioneers of the general system theory. In 1945, he introduced models, principles and laws that applied to generalized systems or their subclasses irrespective of their particular kind of the nature of their components elements and the relation of forces between them. He also composed a classical law of thermodynamics which might be applied to a closed system but not necessarily to an open system. His mathematical model of an organism's growth over time was published in 1934 and is still used in today. In the late 1940s, we see Norbert Wiener and Ross Ashby pioneered the use of mathematics to study system of control and communication, calling it something called cybernetics. Now, the history of system is something which carries on from there, but this is just to give you an idea about how the system started from Sadi Carnot and went into several other mathematicians, physicists, computer science, mechanics, and other things, and the concept of system evolved. Now that we have understood that what is a system, the time is that what is a system that we call in terms of physics. So in terms of a system in physics, we will take 3 points. First is that a classical system, a relativistic system, and a quantum system. Classical system, as we all know, is a very deterministic system where you are given the initial conditions. We can easily determine what is going on. A relativistic system, which is also kind of a deterministic system, and quantum system, which is not at all deterministic, but I would say it is probabilistic. Now, so what we see over here is that a classical system emerges and stems from Newtonian mechanics. Relativistic systems evolves from Einstein's special and general theory of relativity, and it actually is the geometry of space-time. And quantum system emerges from Schrödinger's equation, Heisenberg's uncertainty principle, where we are not given a particular point or an xy axis, but we are given a kind of a wave function which determines the probability of the location or the behavior of a quantum system. Now the question is that when we are talking of relativistic system, can we talk or can we tell that general theory of relativity is completely relativistic, or it has got some other features and behaviors? Let us look into the next part of the video. Is general relativity in true sense relativistic or not? So if we take the components of special theory of relativity, which are, for example, relativity of simultaneity, it leads to length contraction, time dilation, relativistic mass, universal speed of time, and most importantly, E equals to mc square, which is the mass energy equivalence. Now, taking all these aspects of special theory of relativity, what we can tell up till this is that these are relativistic in nature. That means these equations or the mathematical formulations, ideas, all of them are coming from Lorentz transformation. I hope I don't need to explain anything about what is Lorentz transformation, because you already know. So these are the things which are called relativistic because we are using Lorentz transformation, Lorentz boost, and certain other factors which are truly linear in nature. Now, linear in nature and non-linear in nature, we will come to that later, but we understand these things are linear in nature. Now, what we see next is something which comes from general theory of relativity. Components and aspects and features are gravitational time dilation, gravitational waves, frame dragging, black holes, singularities, and event horizons. Taking all these things together, what we see here is that these things are covariant in nature. Well, if you don't understand covariant, I would like to say simply that if things moves in this direction, the exact result or the other thing also moves in that direction. Don't worry, we will explore more about the covariant theory of gravity in this series of general theory of relativity. But most importantly, these are non-linear in nature. That means it doesn't move in a straight line, or it is typically, by definition, it is non-linear in nature. So you see right at this moment we have got a marked difference between special and general theory of relativity. A special theory is covariant in nature. Special theory of relativity depends on Lorentz transformation, and it has got relativistic aspects, whereas general relativity is mostly covariant in nature and it follows the non-linear in nature. And non-linear part. So from here what we can get is this one, that if I take the relativistic effects of special relativity, which are length contraction, time dilation, etc., and then from there if we generalize, because we know that how special theory of relativity got generalized into general relativity, what we get is a curved space-time. And this curved space-time actually causes a huge paradigm shift in terms of moving from relativity to geometry, paradigm shift from a complete change in mathematics, and a paradigm shift in terms of our understanding of coordinates and how it changed. So what I am trying to make a point is that the effects and the ideas of special theory of relativity, or those which are relativistic in nature, is now getting changed into something which is called a geometry, which has got a complete change in mathematics and which deals with curved space-time. Now, when we talk of geometry, we have to keep few things in mind. Number one is this one, which is called, you need to absorb or learn geometry first before going into general relativity. Uh, Please do not jump directly making the calculations of tensor calculus or Christoffel symbols. This is the biggest mistake you make. You should have the ability to visualize things, because general theory of relativity is more intuitive in nature, and you need to have a very good visualization abilities, and also you need to conceive abstract ideas. Now, why I am saying all? Because we are moving from a pure mathematical relativistic equations to something more abstract, something which requires visualization. So just a note of caution to let you know that do not jump directly doing the mathematics of general relativity. Rather, first try to conceive, get the idea, and try to visualize these things are. And that is why I call them, you need to have an intuitive mind, and general theory of relativity is more intuitive rather than being mathematical. So taking these things together, what we can understand that we are delving more into the geometric structure rather than pure mathematical relativistic effects. What is the geometric structure? That is called a geometry of space-time, coming up in the next part of the video. So what we see from here is general theory of relativity is basically more of a geometry rather than relativity or simultaneity. Point number two, which is very important, is that it primarily deals with geometry as an intrinsic nature of space-time rather than extrinsic. That means intrinsically, by the nature of space-time, general relativity considers the nature of space-time as a geometry. It is not an external or an extrinsic object. So from there we can deduce these facts that parallel transport, covariant derivative, Christoffel symbol, geodesics, curvature tensor. Although I have talked earlier in this video, but in this fresh series I can tell you that we will be covering those things. All those things tells us, one, it has got a geometric understanding. Two, it has dealt with understanding of curvatures. It is more intuitive in nature, and that is why we need an exotic mathematics, which is not which really doesn't work out with the existing mathematics of calculus or differential calculus that we know, but we need a different kind of a mathematics. So till this point of the video, what I'm trying to make an establishment of the point is that when we are going into general theory of relativity, mentally we have to be aware and we have to understand that we are dealing more with very abstract ideas. Things are more depending on visualization rather than taking up a pen and a paper and doing the straight away mathematics. So from here, where do we come? We come here. So all these aspects, ideas, consequences, results of special theory of relativity, when they get generalized into a much broader aspect, which are tensors and geodesics and Riemannian curvature tensor, what we see is that there's a huge transition, and this transition is nothing from relativity to geometry, and this has got a less of a relativistic effects and more than of a nature of space-time. Now the thing is that, as you can see, that we have already started with what is called a geometry of space-time, and we have already established the fact that what is a system. Now we need to understand one thing very closely, which is very intrinsic, which is very deep, that because general theory of relativity is a classical system, we call it more of a classical physics. Question is that how and where can we define what is a classical system? Coming up in the next part of the video, what is a classical system? Not Newtonian mechanics, not throwing a cannonball, but something very deep, and I'm sure that you will enjoy this part. What is a classical system? Now all those figures that you see on the left hand side with Isaac Newton and then others like Maxwell and Faraday and Einstein, they are all classical physicists. So classical physics means that it would deal with a set of rules. Number one, obviously, there will be a set of principles and there will be an underlying logic. And finally, what we can say is that these are the areas of classical mechanics, which says that these are deterministic as well as reversible. I will explain you, don't worry, what do I mean by reversible, but these are all deterministic and reversible, and it can predict the future and how the set of events will behave. That means given a set of conditions, classical mechanics or a classical system would be able to predict how the next few events would be. I would like to demonstrate what is a classical system with a very simple example. So we begin with a simple trivial example, and let us imagine that this is a kind of a system which is pointing somewhere, which has got a charge, etc. And this is obviously a non-relativistic system, and this is a closed system. That means nothing external interferences disturbs it. Now we would think of something, so it doesn't exchange any matter on the surroundings. Now we would think this one as a coin glued to the table. Forever it will show heads or tails, doesn't matter, it is showing a tail. So in the physics jargon, the collection of all states by a system is its space of states, or we can simply say it is a state space. Now because this has got a head or a tail, whatever you can say, the state space is not an ordinary space, it is a mathematical set whose elements label the possible states of the system. Here the state space consists of a single point, maybe for example the heads or tails, and this is the state space. So the future will only predict head, head and head. And if it is a tail, it will only predict tail, tail and tail. Because the system, remember, has only one state. Predicting the future of the system is extremely simple. Nothing ever happens and the outcome is always either the heads or the tails. So this is why it is called a single state system. So remember, the state space is not an ordinary space. It's a mathematical set whose elements label the possible states of the system. So if it has got a coin which is glued to the table and it is pointing upwards to the head, then always the state space will be heads, 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 or if it is pointing towards the tail, it will be tail, tail, tail. And this is a simple system which is called a single state system. Now the next simplest system has a state space which consisting of 2 points. In this case we have one abstract object. For example, imagine a coin which can have a head and a tail. In classical mechanics we assume that systems evolve smoothly without any jumps or interruption. Such behavior is said to be continuous. So obviously you cannot move between heads and tails smoothly. Moving in this case necessarily occur in discrete jumps. So let us assume that time comes in discrete jumps which are labeled as integers. So from head we can go back again to the head and we will only have head, head and head, and from tail we can go back to the tail and then we will have only t, t, t or tail, tail, tail. So in this case, for example, if we get a system which is changes, for example, with time, here is a clock and here is a system that changes with time, this is called a dynamical system. A dynamical system actually consists of more than a space of states. It is also entails to the law of motion or dynamical system. So from here what we see is that we can find out that dynamic system which is opposites. So from head, say for example, if you are going to the tail, and then from tail we are going to the tail, we can still predict that we can say that these numbers may be from head to tail, we call it sigma, and we just name it as a possible value of 1 as 1 from head to tail, and from tail to head we from head to tail it is -1, and from tail to head we call it as 1. I'm just using a symbol just to make things pretty easy. So what happens is that from head to tail, if I start my journey, predicting the future again becomes easy. So HT, HT, HT and so on. And if I start from tail, it will be tail, head, tail, head, tail, head and so on. So we are using this symbol sigma just to keep a track. So when we are considering a continuous evolution in time, we can symbolize it with T. However, this is known as the degrees of freedom. That means the number of independent parameter that defines its configuration of the state. So degrees of freedom means the number of independent, how many parameters a state or a system consists of. So we are writing time equals to t because we just need to symbolize it, and here we use a discrete evolution which is denoted by this symbol n. So the state of the time n is described by the symbol which stands at n. So what we can do simply is that we can write those equations as something like sigma n plus 1 and equals to sigma n, and for minus we can write as this. So this is, I would say, a kind of a very simple example of how the things are evolving over the space and the time, and what is a system is all about. To make things a little bit more complex, let us imagine that we have got a cube, and if you try to analyze the cube, then we see that you can go from 1 to 2, 2 to 3, 3, 4. So these have got 6 options and 6 states, and from here also we can do. So this is, say for example, we call it as dynamical law 1, right? So instead of a coin, we are taking a 6-sided die which has got 6 possible states. And to make things more complex, we can go from 1 to 2, 2 to 6, 5 to 3, and this is also a kind of a system. So you see we can come back, and this is called dynamical law 1. So for a 6-state system, we have a 6 possible states. For other state system, we will have things like other. Now, say for example, we come to know, we told that is a classical system is something which is reversible in manner. What do I mean by that? A dynamical law must be reversible. So if I get a system where from 1 to 1 I can go to 2, from 2 I can go to 3, and from 3 I can come back to 2. This is the system. Now, so arrows are reversed, but this the result is still deterministic. Now what happens if I suddenly stand at here? That is at state 2. Now if I ask you a question, where were you just before coming to state 2, you won't be able to answer, because there is nothing which goes from 3 to 2. We cannot go back, and there is nothing also from 1 to 2. You are just at position number 2. So what do we call that? You cannot go back from 2 to 1. So this is not allowed, and this is what we call, there must be one arrow to tell where you are going and one to tell where you come from. If this type of a thing happens, this system is called an irreversible system. That means you cannot tell where you are at the past or where you are going to the future. So this is also another state. The system is irreversible. So state 1, as you say, has no past, and there is no state which leads to 1. So this is called an irreversible system, but classical system, remember, is a reversible system. That means we can go back from where we came. Okay, now here is something very interesting which is called the conservation laws, and I will like to show you. Say for example, we give each cycle a numerical value. So from 1, if I'm going back to 1, and from 2 again I'm going back to 2. And here I would like to tell you that we have got this one from 4 to 3, and again I am coming back from 3 to 4. In the examples of these 3 cycles are labeled as, so state spaces is separated into several cycles, and each cycle has a dynamic rule and it belongs to its own circle. So 2 belongs to 2, 1 belongs to 1. So whenever a dynamical law divides a space, I would say the state space, into such separate cycles, there is something which is called a memory, and this memory is called a conservation law. So from 1 to 1, if I'm going back plus 1, and then I'm going back to minus 1, and from 0 again I'm going back to 0, we can name these states as q equal to plus 1, q equal to minus 1, and q is equal to 0. So what do I mean? That whatever the value of q, it remains the same for all time, because the dynamical laws does not allow jumping from one cycle to the another cycle. Simply what we say is that the q state is conserved. So I would repeat, whenever a dynamical law divides a state space into such separate cycle, there is a memory. Now we have named this as q equal to 1, q equal to minus 1, and q equal to 0. So whatever the value of q, it remains same all time, because the dynamical law doesn't allow you to go from q to q1 or q2 or q3, which you saw earlier. And what we see is that allowing jumping from one cycle to another is not allowed. And that is why we say simply that state q is conserved. This is very deep, this is very fundamental. Conservation of law means that the state in which it is occurring, it remains there. Now, having understood what is, I would say, a conservation of laws, what is a system, and what is a classical system, now it is time to look into what is called okay, so yeah, whatever the value of q, it remains the same. Now it is a time that we should look into something which is called a deterministic and a non-deterministic system, because what we saw is a deterministic system because we can determine and it is even reversible. It is not irreversible. But there is something which is called a non-deterministic system which eludes the concept of general theory of relativity. What is that? Let us look into the next part of the video. Typically, for an event in any Cartesian coordinate, we are given 2 points, say for example any coordinate, and we can just predict anything. But in case of this kind of a wiggling wave on the right hand side in green which is written, we can tell that the position or maybe the subatomic particle, for example electron, it can be here, it can be here, it can be here, it can be here. We cannot say for sure where it is. So this is actually denoted by the Greek letter psi, and it tells that it is a variable quantity that mathematically describes the wave characteristic of a particle. If you want to know more, you can go back to my videos on quantum mechanics in my Physics for Students channel. You will find it. So the value of the wave function, even if we square it, it gives a particle at a given point, I would say a likelihood, just a probability that this particle can be around this zone. See, there is a marked difference. The left hand side says that we can deterministically and for sure we can find where the particle or how the system behaves, but here we can only say in terms of probability. So using Max-Born statistical interpretation, what we can say is that probability of finding the particle between this. So here is a kind of a wave, I would say probability amplitude, and the points are A, B and C, and this dx, this brown zone, this one actually tells that this is a probability. I cannot tell, but it is just a probability of finding the particle more around A but not around B and C. And this is called indeterminacy, an inherent property of quantum mechanics, and that actually made our Dr. Albert Einstein very, very unhappy, and he used this famous term, God does not play dice. So you can look into my video where I have elaborated on the philosophical interpretation of God does not play dice. It is there in my Physics for Students channel. You can have a look onto it. So now it is the time that we have understood what is a system, we can understood what is determinism and what non-determinism. Based on this deterministic behavior, general theory of relativity tells us few interesting points, few interesting interpretations and few interesting predictions. What are those predictions? What are the important points that we will cover up coming up in the next part of the video? These are certainly called the predictions of general relativity, or in some other way. The first thing which calls is the equivalence principle, where it tells that in general relativity is actually rooted in the equivalence principle, which posits that there is no experiment that can distinguish between an observer in free fall, that is in a gravitational field, and an observer in an accelerated reference frame. In other words, gravity and acceleration are indistinguishable. This concept challenges the traditional Newtonian concept of gravity as a force. We also see curved space-time. So according to GR, massive objects like planets and stars cause space-time to curve around them. Instead of gravity being a force that pulls objects towards massive bodies, as described in Newtonian gravity, objects follow curved paths in the curved space-time. We also find something which is called a geodesic, where objects are falling in unaccelerated, or I would say non-accelerated to be technically correct, motion in gravitational field, and follows the paths which are known as geodesics, or the shortest path in a curved space-time. This concept emphasizes that objects move naturally along paths determined by the geometry of space-time. There is something which is also called warping of time, because GR predicts that time is affected by gravity. Clocks in stronger gravitational fields run slower compared to that in weaker gravitational fields, and this effect, known as time dilation, has been verified experimentally many times. GR also takes into account there is no concept of absolute space and time. This is a corner which was a cornerstone of Newtonian physics. Instead, it suggests that the geometry of space-time is relative and depends on the distribution of mass and energy. GR presents gravity as a consequence of the curvature of space-time rather than as an external force. This view provides a more profound and elegant explanation of the gravitational interaction. Now, why I showed you what are the predictions of the components of general relativity? Because these are the areas, these are the basics on which the entire edifice of GR stands, and in due course of this series of video, we will explore each of these components. Now is the time that we should now prove and now tell you why I have been telling you system and system, because I want to show you that why general relativity is a classical theory. We need to understand that very strongly, and based on the ideas of classical theory, once we move into the mathematics, things will become clear. Why general relativity is classical theory? First of all, let us understand that we have clearly understood the difference between classical and quantum theory. One is deterministic, another is non-deterministic. There are a lot of inherent, I would say, indeterminacy inside quantum theory, which is not present in classical theory. First of all, we need to understand that general relativity is a field theory. That means if I'm taking this kind of an area, a field, and there are various things which are like a magnetic charge, an electric charge, a stress tensor, gravitational field, all of these actually are describing how physical quantities behave through space and time. So if I take all those things, field theories are those that describe how physical quantities, you see each of these are pointed, that means are deterministic because the value of the field at each point, those black I would say balls in space and time, can be uniquely determined from the field's equation of motion. So on the right hand side you see it's a generic field which consists magnetic charge, electric charge, stress tensor, gravitational pull, etc. And here it says that this is deterministic because the value field of any point in space and time can be determined by the equations of motion. Also, Einstein's general relativity is deterministic equation because it comprises of what is called the Einstein field equation. These equations relate to the curvature of space-time, to the distribution of matter and energy in the universe. That means if I'm given this kind of a space and if I'm given the initial conditions, that is matter and energy distribution, then the equation would tell me, rather tell you that to determine the future behavior of space-time geometry with certainty. So the deterministic equations, be it Einstein's field equation or anything, means that if you're giving an initial condition, that is the distribution of mass and energy, then through these equations you can very well detect the behavior of the space-time geometry, the future behavior of the space-time geometry. Also, we need to understand one thing very closely, that there is a lack of inherent probability. What do I mean by that? I mean to say that in classical physics, including general relativity, there is no inherent probability associated with the fundamental equation, which is there in Heisenberg's uncertainty principle and various other things, that this is inherently you cannot determine it is probabilistic. So the behavior of particles and objects and the curvature of space-time is determined solely by the initial conditions, just as I showed you, and the equations of motion, and there is no probabilistic elements. There is no inherent probability that would say, no, it might happen this, it might happen that. No, it is not. It is behavior is absolutely determined by the initial conditions, and we can predict the future. Also, there is something which is called conservation of information. Deterministic systems like general relativity and others preserves the conservation of information. This means that if you know the complete state of the system at one point, you can in principle predict the system at another point, and there are no loss of information of the probabilistic guesswork. So that means what I can say, that the evolution of space-time and the motion of objects can be very well and easily determined with precision. We also see that it has got a predictive success. That means general relativity has been extraordinarily successful explaining the predicting of a wide range of astronomical and cosmological phenomena. The precise predictions of general relativity, which we will see later in this series of video, like bending of light, properties of black holes, etc., have been confirmed by extensive, I would say, experimentation and observation, further emphasizing that yes, it is a deterministic nature. Causality and determinism. Well, causality is the principle, I would say, that every event has a cause. As you can see, this is a light cone. So causality is encoded in the light cone structure and space-time. The light cone of an event is a region of space-time that can be causally influenced by an event, or we can say, in other words, any event outside the light cone of an event cannot be caused by an event. Determinism is the principle that the future states of a system is uniquely determined by its current state and the laws of physics. So general relativity is deterministic because the evolution of a space and time of the motions of objects are uniquely determined. Here is a kind of a what I would say a clean summary of what I just talked. General relativity is a deterministic system that adheres to the principles, and the present state is uniquely determined by the past state and the laws of physics. So here is a quick summary of today's lecture, what we have learned. So from today's lecture, what we can say is that we understood what is a system. We understood what is a system in physics and general relativity. It is not purely relativistic, but it is more of a geometry of space-time. What is a classical system? What is the difference between deterministic and non-deterministic? And we have established the fact that general relativity is indeed a classical theory. So most importantly, if we would have not established the fact that GR is a classical theory and understanding deeply what is a classical system, hence we cannot proceed to the next level, obviously. So the most important part of this lecture was proving GR as a classical system, understanding what is a classical system, what is a determinist system, what is a reversible system, and most importantly, the method and the learning of general relativity is not like special relativity, not too mathematical, but it will be on the geometry of space-time. So that's all. I would like to thank you immensely for watching this video. Please don't forget to subscribe to my channel Physics for Students and click on the bell icon to get all the notification from Physics for Students. This is my email ID and my other channel. You can follow me further on my Facebook, LinkedIn, and my Instagram and Twitter account. I would be soon coming up with the episode 2 of General Theory of Relativity, and this is an exclusive series which will be sequentially covered, as I told you right at the beginning, and I will continue making more and very detailed videos in this series, followed by other videos. Thank you very much for watching.